Okay, so let's look a little bit at the meridional energy balance. First, we should remind ourselves that any model we do must include seasonality, because one of the main features of meridional energy transport and hence energy balance is that there's a strong seasonality in it. So we are looking at all the terms here, the mean and the transient eddies, stationary eddies, and the meridional flow. But you see that during the winter, or the winter hemisphere tends to have maximum transport during that season, because, as we said, the equator to pole temperature gradient is the strongest, so energy transport is the largest. So you can see June, July, August, and DJF, the differences are quite large here, even though for the southern hemisphere the terms are differently distributed because of the Southern Ocean and so on that we talked about. So what is the meridional energy balance model? We remember that the temperature gradient goes from high in low latitudes to low at the poles in the northern hemisphere, so it's a negative gradient. Our y coordinate or latitude coordinate goes from the equator to the north pole, whereas it is negative from the equator to the south pole. So the temperature does decrease in the southern hemisphere as well from the equator to the pole, but the gradient is positive because we are going in the negative direction, right? So we have to keep this in mind when we do the mean energy transport. So there is a negative correlation between dt dphi and the average transport in space and time. So here we are averaging in time and space of the zonal mean, vertical mean, meridional velocity, and energy density. We can write this as flux rho c times v prime t prime bar. So we are doing the mean of the eddy component and multiplying it by air density and heat capacity. We can now use things like what we did before, the fact that these are negatively correlated. We can write the parameterization as minus rho c times some diffusion coefficient k that is dependent on latitude times 1 over r, where r is the radius of Earth, times dt dphi, where dt dphi is of course the meridional temperature gradient, which is negative in the northern hemisphere and positive in the southern hemisphere. So that's a very simple way to represent the eddy components. It has been empirically shown that this equation is valid for time scales of greater than 6 months. So you have to average long enough, because there is an inherent transportation time scale involved from the equator to the pole. So the eddies have to be averaged long enough before a simplifying parameterization gives you the right value, and it has to be averaged on a large enough spatial scale as well. And that scale turns out to be 1500, order 1500 kilometers. This was shown by Ed Lorenz again in 1979. There is a Lorenz energy balance model that you can look up in terms of how the terms radiative forcing and other forcings get moved between each other in the climate system. So we are now trying to do the original one-dimensional energy balance model. We looked at the averaged global energy balance in terms of 4 pi r squared. R is again the radius, h is the scale height of the atmosphere. We had set it for 8.2 kilometer or so. Density, heat capacity times dt dt, where this is the time rate of change of our averaged column of air, is pi r squared 1 minus alpha S0. This is the energy that is being received from the sun, and we have to balance it with the energy that is going out. And we had assumed that the surface is a or the emission is happening from a gray body with emissivity of epsilon, so we are emitting everywhere, so 4 pi r squared times sigma T to the fourth, where T is our emission temperature. So we can now write this equation as HRC dt dt, take out pi r squared, bring out the 4 here, so we have H over R cosine phi dd phi of rho c k phi 1 over r dt d phi times cosine phi. So we are basically writing this into our balance equation now, plus 1 minus alpha, and albedo is also made a function of latitude, which is realistic, divided by 4 times s phi. So latitudinal dependence of solar energy is also considered, minus epsilon phi, so emissivity is also a function of latitude times sigma T to the fourth. So this is consistent with latitudinal dependence, and that allows us to also make seasonal dependence of our energy balance, right? So the simplest way to write the latitudinal distribution of solar energy coming in is to take the solar constant at the top of the atmosphere times some constant 0.5294 plus 0.706 times cosine squared phi. So at pi over 2 this can go to 0, and depending on the season it can have a certain value, as we know, right? So this is a second order equation. So we can you can see that here d d phi of dt d phi, so you're going to end up with something like d squared t d phi squared. So that's a second order equation. So it will need two boundary conditions, and you can make the heat flux disappear at the temperature gradient disappear at the poles. So dt d phi latitudinal gradient can be set to 0 at the south pole and the north pole, right? So pi over 2 and minus pi over 2. So that solution can be written for the estimated value of k phi. So in this equation we know the gradient, and we can estimate the value of k phi, which is to the of the order of 10 to the 6 or 10 to the 7 meters squared per second, I think. Okay, so this is a simple energy balance model. It is called the Burico energy balance model. Was implemented first by Sellers, and I should mention the names here just to be sure that I didn't so this is the Burico-Sellers model. Burico 1969 and Sellers 1969 were the first to propose such a simplified climate model and to address fundamental questions concerning climate change using this model. Okay, did I miss anything else there? K, everything is function of latitude. Okay, so here we have the simplest energy balance model that now takes, you can also expand this into 2 dimensions, and we will do that when we look at the energy transport in the ocean. For the atmosphere, it makes sense to make zonal mean and look at the meridional transport, but the ocean, as you know, has boundaries. So we have the Pacific Ocean, the Indian Ocean, and the Atlantic Ocean. So making zonal mean in the ocean often is not as sensible as or not as appropriate in terms of simplifications as making the zonal mean in the atmosphere. Atmosphere has no boundaries, winds can go around, so it's easy enough to think of zonal mean meridional quantities and vertically average quantities in the atmosphere, but that's not necessarily a good way to do things in the ocean. Okay, so let's leave it here with the Burico-Sellers model, which has been used. Obviously we should remind ourselves that in the real models, I mean the full atmospheric GCM models, even if it is just the atmosphere and is being forced with some kind of a prescribed land quantities and prescribed sea surface temperatures, it can still do the energy transport as long as the ocean is also implying an energy transport by prescribed sea surface temperature gradients and so on, and seasonality if you want to get the seasonality of the energy transports. So the model will do all the terms. So in the model we can estimate its mean and stationary eddies and transient eddies and so on. So in the full model we don't need to parameterize these things. These parameterizations are when you are not running a full model and are trying to look at implied meridional diffusion of heat in this sense when you change the equator to pole temperature gradient, for example, in the glacial deglacial situations at long time scales. Before, in 1969, no models were being run for paleoclimate simulations. The atmospheric and oceanic models had just started. Kirk Bryan and Suki Manabe were just setting up these models and testing them and so on. Coupled models were just being proposed by Suki Manabe as the only way to do climate studies and so on. So these models were used in the context of glacial deglacial type studies where orbital forcing changes the distribution of solar radiation, albedos because of glacial or deglacial times, and change the equator to pole temperature gradient. So you want to understand the meridional transports of heat, and in those situations this kind of a simple parameterization is really useful. Okay.